Thanks. My name is Hui Zhou. I'm from the MPICH team. I'm one of the co-developers at Argonne National Lab. Today, the topic is MPI+Thread, and we'll talk about some recent proposals and extensions we made in MPICH that to help MPI to collaborate with threads and let them work together in a complementary way rather than in a compromising way. So first, an overview or simplistic view of what is parallel computing. And the goal in parallel computing is to keep each parallel units in either process or threads to run at full speed or maximum speed. And the enemy here is the synchronization. The synchronization will significantly slow it down and kill your performance. And unfortunately, most practical parallel computing tasks will require frequent synchronizations. Thus, how to manage synchronizations is the core task of parallel computing. So here are some, we're going to talk about MPI and OpenMP and maybe touch a little bit on the GPU runtime as CUDA. So here is putting some elements, listing some elements here, so putting these into some context. So first, the first out front elements is you need to write the parallel codes. And the window here is that we write a single program and then run with multiple data. The MPI, OpenMP, or even the GPU runtime such as CUDA all fits in this paradigm. Next, this is the most significant for the users. You need to get your code into this parallel environment. How to launch it, and usually this is the most difficult part for the users. You know, you advertise certain great features, but you can't get into it. So we have different ways. In MPI, we rely on the Java launchers, and we call it a static launch. And once launched into this parallel environment, it's rather inflexible and it's fixed environment. On the other hand, the multi-threading runtime can offer the dynamic spawn method, which offers a more flexible way. And I put a stars here. I think the user obviously would prefer this method. And then in actual parallel programming, we need for correctness, we need to avoid data races. And for the CRUD method, you can apply critical sections. As we said, this is the enemy, and it will kill your performance. And the better way is to privatize the data. Then you don't need critical sections, and the private data will never have data races. But in order to, we still need to manage the synchronizations, and for shared memory parallel runtimes, we can use these basic elements such as barriers and mutexes or atomics. But MPI offers better, more higher level APIs such as message passing and higher level collectives. I put a star here as a I'm from the MPI developers, so I'm obviously biased here. Here's the same information. I just put in this runtime in a different way. So as I listed here, from MPI point of view, the thread runtime shares a lot of similarity to the GPU runtime. They're both using shared memory, and they both have dynamic launching method and spawn method. And they both are using the implicit critical section kind of based synchronizations. So for this talk, I mostly focus on MPI with collaborating with threads, but the solutions we proposed and the framework, the lessons we learned can easily extend to MPI working with the GPU as well. So let me go back a little bit. So as I listed here, MPI and OpenMP have advantages and disadvantages. And from user point of view, obviously, we always trying to at least attempt to reap benefits from both worlds. And this end up with MPI+Threads, which is dominating paradigms for the last couple of years or decades. Unfortunately, MPI+Threads is rather compromising paradigms. So it's shown here, the threads and MPI actually lives in rather separate world. And the threads cannot take advantage of the MPI's message passing for synchronizing between the threads. And the MPI cannot take advantage of the thread runtime to expand its parallel environment. And also, which is most damaged of all, MPI loses its immunity to data races, so it has to add the critical sections, which kills the performance and ends up with miserable performance, notorious performance for MPI thread multiple. So here we need to mention the MPI thread levels. So MPI thread level is not really an effort of collaborative effort between MPI and the thread. It's rather what I show here is a tug of war on convenience between application layer and the MPI library. So for thread single, thread funneled, and thread serialized, the application layer is managing the synchronization, and MPI get to still, assume the serial model and easily obtain or maintain its high communication performance because it doesn't need to worry about the data race. But for MPI thread multiple, there's we place no restrictions on the MPI on the application layer. But that doesn't mean the whole program is free of synchronizations. So what ends up is we push the burden to the MPI library. And it turns out the library has more difficult job to do this than your application layer, because from library, we don't see threads, and we cannot tell what is the context, which thread from, one thread from the other. So that tends to end up with miserable performance, but there's opportunities. We'll touch on this later. So just lay out the what we starting point is and showing how miserable this is. So this is showing two processes on a single on different node, and they are passing messages. And with the single thread, we have very decent message rates. And as soon as we add a thread and multiple threads start to concurrently send messages, they start to contending on each other, then the aggregate message rate starts to slow down, and it gets worse and worse as we add in more threads. And be noted that what we're showing here is the aggregate message rate. So if we look at the per thread message rate, it's even much worse. All right, so this is going on for past 2 decades or so, and how did the application still tolerate MPI? Why they still use MPI? Turns out there are workarounds. So that I listed 2 workarounds here. The main one, the first one, if you're using multi-thread, try to avoid small messages, and if you're using large enough messages, you can saturate bandwidth. And so as the graph showing here, the per thread bandwidth still suffers, but we are saturating bandwidth. You cannot do any better anyway. So that's application understands and goes by. Alternatively, you should avoid threads and deploy multiple MPI process on a single node, ideally matching 1 process per core. That way, MPI still maintains its without immunity to the data race, and it's able to easily obtain, as shown here, a very scalable performance, communication performance. So both workarounds nowadays, due to the development of the modern HPC architecture, are less applicable today due to time constraint. I'm not getting into it, but you can ask me in the coffee break. So here is also, I'm going to go pretty quick here. So showing why the performance is so miserable, because MPI has to place the global lock for correctness, and not only it serializes your concurrency, parallelism, it also adds contentions to it. And historically, this is because in the hardware layer, we only have a single network endpoint, so you're going to be serialized anyway. So a global lock makes sense, and it's more efficient if you more efficient than place the multiple locks. But things are changing. Now the hardware layer usually support multiple network endpoints. And so the natural solution is to split your internal resource into multiple, what we call here is inside MPICH, we call it virtual communication VCI, virtual communication interfaces. And in ideal world, it's much easier to plot here than to realize in practice. But I'm going to just talk about it. So in the ideal world, when the user layer threads perfectly match the internal VCI, and the internal VCI perfectly match the network endpoints, then all the parallelism will be conserved, and it will retain the ideal, or at least obtain the ideal performance without any slowdown. or with minimum slowdown, I would say that. But this is much easier to draw than to implement. And the reason is you have to remember at the MPI library level, we don't see your threads. You just directly call us from your context, and we cannot tell which context is this, and you never tell me. And the most important of all, in the MPI standard, we are bounded by the MPI specification, and in the MPI specification, there's simply no such concept as MPI as thread. There's no foreign runtime. The only execution context is MPI process. So we have to hack it. In MPICH 4.0, we realized the existing MPI standard does have, in a message envelope, there's a few extra leeways. The envelope consists of a communicator, tag, and ranks, destination rank and source rank. And these can be somehow hacked as secret signals to us. So as any secret language goes, right, you have to agree between the application and the library. But once you agree, you can use them to pass signals to us. For example, if you each thread using different communicator, and we agree on this, then we can assign different VCI to different communicator. Then we can manage to maintain your parallelism. But if you don't know this secret language, or you are using different settings and different libraries, and we don't agree on this secret language, of course, everything's going to fail. So that leads to, it's a hacking solution, right? So that leads to, if we really want to solve this, we really need to address the problem from the root. And the root is MPI does not know about your thread context. So here is the proposal, and it's currently implemented as extension in MPICH 4.1, which is already released last November. So we propose a new object, MPI object, called MPIX stream. MPIX stream identifies a serial context, execution context. You can create them using these APIs. And you can customize them using info hints. By default, if you don't provide info hints, like using MPI info now, they are just a CPU thread. But you can say, this is not a CPU thread, this is a CUDA stream T or HIP stream T or whatever your extra runtime. We may not understand it, then we ignore it, right? But if we understand it, in this case, we understand the CUDA stream, then we know all the consequences, all the side effects that you mean by using this stream. So the way to use it is you create the communicator as usual, but you apply this, each process is going to apply its local stream. So stream is a local object, but the communicator is not. So each process attach its local stream to the communicator, and this communicator will know all the local stream information, global stream information from the communicator. And you use the communicator regularly as your normal MPI does, the MPI send, MPI or reduce. All these will work as normally with the same syntax, but MPI library now just has extra information and know what your thread context is, and we will do optimally as you say, as you instruct us, rather than through secret language. This is an agreement, like a public agreement we'll both bound by. So as I said, it can extend to the GPU runtime. Of course, the GPU runtime will be slightly different. In this case, for the CUDA stream, it's always asynchronous. So there's this kind of in-queue semantics, extra semantics to it. Even though, as you see, the signature is exactly the same. Here, MPI send in queue is exactly the same as MPI send as far as MPI goes. However, the CUDA stream added this in queue semantics to it to avoid the confusion in your code. We always like explicit code, right? So we added this some kind of alias to the function name, API name, called MPI send in queue. But for an MPI, it's just MPI send, but it adds the in queue to the stream semantics here. So I go rather quick here. All right, so just as a result, what we did here, started with very miserable performance. Then with implicit mapping through magic secret language, we are able to demonstrate that you can achieve a very good scalability using MPI thread multiple on small messages. However, this is very delicate. It depends on this secret handshake, right? And not handshake, secret agreement. But with the MPI thread, MPIX stream, application are able to robustly obtain the same scaling ability. And with the 20% even better performance. The reason is now we agree, we know you are in the serial context. We really don't need an extra lock to protect it because you already managed to protect it already. So we can remove the locks, and removing the lock, even non-contented lock, gains the 20% communication performance here. So MPIX stream improves the MPI plus threads. However, MPI and the threads are still not collaborating. Okay, so inter-threads, for example, the inter-threads communication cannot use MPI, and MPI cannot utilize the thread's ability to expand its runtime, expand its parallel environment. And also, the similar tasks, like collective tasks, often are reinvented in your thread parallel region, and which MPI already solved for you. Case in point is PETSc here. PETSc folks are very clever folks, smart folks, and effort diligent folks have tried but give up, and MPI has won. And now PETSc only uses MPI everywhere. But users still want OpenMP, and due to the recent architecture evolution, right, it's more important to acknowledge this. Then the question comes, user will ask, request for PETSc folks, how do we do OpenMP plus PETSc? So let's introduce some new things or new paradigm. So here are we introducing, instead of MPI plus threads, we call it MPI multiply threads. So you start with 4 processes, for example, and each process launched 4 threads in your OpenMP parallel region, and we merge them together and create an MPI multiply threads environment where each thread behaves as a single MPI process within your parallel region. So if essentially you end up 4 times 4 equal to 16, that's what the name multiply refers to here. So here's the API, how to use it. So outside of the parallel region or in your master region, you initialize this thread com called MPIX thread com init, where you specify how many threads your local process gonna use. Then inside the parallel region that matching this number of threads, each thread, so there's different number of threads are calling, okay? Each thread are gonna call the start and finish. And between the start and finish, it's just a regular MPI communicator that you can use. And if you're familiar with MPI, you should be able to do this. And what is noted here is you can do any thread to any thread communication here. Here showing some results. So here is the 2 process on the same node, and so MPI everywhere versus a single process, but launch multiple, create a multiple thread parallel region, and then create a thread com, and end up using the same MPI functions and measuring the latency and the bandwidth. We'll see they have great match, and as long as semantics matches, technical always converge, right? Eventually they're gonna reach the exact same performance, but here is showing a slightly improved performance with thread com. The reason is I shortcut a lot when we implement the thread com because the thread com is new and it can regard a lot of corner cases in the MPI. So these shortcut hacks allows it to have a better performance. But eventually, when all the semantics solved and all the technical problems solved, they should have the almost same, nearly same performance. Now here, what we want to show is with MPI plus threads, it's not just the MPI gains things, right? The OpenMP users also gains the MPI toolset. One thing is that MPI offers very high level collectives. Now barrier is not a good case. Okay, barrier is very simple, and showing here the naive implementation. The thread barrier performs much better than the green default MPI implementation. The reason is MPI barrier uses zero-sized point-to-point messages, and the point-to-point messages has a message envelope, so there are overhead against this simple message latency. However, as long as the semantics matches, that's what I want to emphasize. That's the default behavior of the MPI barrier is just technicality. And so I re-implemented the MPI barrier using the exact same dissemination algorithm, but replaced the message-to-message passing with atomics. And then we end up with almost exactly same performance. So just showing we opened the gateway to have OpenMP access MPI and MPI access OpenMP. So that's my point. Now here showing a reduction. And in this case, actually MPI, default MPI performs way much better than the OpenMP. The reason because MPI is, we excel. We have 20 years of experience in these things, but the OpenMP is like a kind of a neglecting. It's just as a convenience offer for you. It never tried to optimize it. But I don't think this performance is really meaningful here. Okay, what I think, there's nothing prevent OpenMP do exactly or use the MPI in this case to implement whatever this is. So the performance difference is not the point. The point is we offer the MPI tool to your OpenMP now. Your OpenMP users, you don't need to reinvent wheels to do the things MPI already do. So lastly, let's show the how to use PETSc with the thread.com. So here's the code, and some good news is Junchao and me spent 2 afternoon hackathon, and we hacked a few things and we get it working, and we have a very good performance comparison, comparing MPI everywhere and single process, then spawn multiple threads using OpenMP only, and then the same code, same internal algorithm, not changing, and it works and it performs well. But there are a few things that we need to be aware. So by default, PETSc is not thread safe. That means PETSc does use a lot of global variables, and those global variables we have to do something in order to make it work. So what we've shown here is we moved the PETSc initialize and PETSc finalize outside of the parallel region. That way you only initialize one version of a global variable. Then we somehow hacked a little bit. Then inside in the actual PETSc calculate computation, we do not write to the global variables. So the global variables is just read only. It's shared. So that way it still works. We have to turn off the thread. We have to add the thread safety. We have to turn off the logging and turn off the debugging. So for long term, PETSc need to be thread.com aware in order for users to use code like this. One way is use thread local storage. And alternatively, you can do global init and read only. And you have to have code place to guard during the actual thread.com region, not to write to your global, because otherwise it's a risk. Or you're just using log to protect your write. You need a mutexes or thread.com aware, what I call, so you understand. You can check. You can call MPIX, say whether it's a thread.com, then you'll know whether you should apply the lock or not. And these lessons we believe it applies to all current MPI only application, and you can naturally do the same thing here, and your MPI only code will work with OpenMP, but just pay attention to your global variables. And the changes are required, take some effort, but compared to the amount of PETSc effort, like past how many effort, right? I think the extra effort to make this work is really minimal. All right, here's a summary. So MPICH 4.0 offers the implicit VCI mapping, and MPICH 4.1 offers the MPIX stream API. And the thread.com communicator is currently in the main development branch, and will be available in MPICH 4.2, and the release schedule is this year, November. Thanks.
Thank you, Hui. That's a very interesting talk with some interesting developments that people should be interested in. Yes?
What implementation of OpenMP did you use for your comparisons?
I'm sorry?
So which compiler? Was it the GCC implementation of OpenMP?
GCC. Yeah, I just used the GCC here.
Okay, thank you.
So that may explain why some of the performance are not so great. Yeah.
I have a couple of questions, but the one that is bothering me is typically MPI is for distributed memory system, right?
Mm-hmm.
And PETSc is in a way biased or aligned with MPI, right?
Right.
So when you integrate OpenMP code that is fundamentally based on shared memory systems, that should cause any problem or not?
It will. So it's showing here, right? So you need to worry about your global variables. So if you are using global variables, like your initialized global variable should be read only during your actual computation. And during incubation here, like the MPIX mat create, right? Your information, you should try to localize it into your object, for example, the matrix A. If you put your dynamic computation required global variable in the variable A, then it's somehow contained in your thread. So that should work.
Another thing you mentioned, MPI stream, the new kind of new solution. So if you have data dependency, it will work the same way, or?
MPI stream don't care about your data. What MPI stream is, you tell me what is your execution context, and you manage your execution context. So if you're using same MPI stream, right, the requirement is you only use any function touching this MPI stream within the serial context. You cannot have concurrent access to the same MPI stream.
Okay, so it's totally serial.
Right, right. So it's basically a clear separation of obligation. Your obligation is to manage the data race, and our obligation is to do the best performance.
And in the beginning slides, you had MPI, OpenMP, and CUDA. But later on, you have not talked anything about CUDA.
No, there is. There's this MPIX here. These are for the CUDA streams.
So PETSc will work with CUDA as well, or?
Basic what?
PETSc will work with CUDA-based code? CUDA.
I do have some sample code with CUDA. I didn't list it here. I already running. I think it's quite a busy time, and but get touch with me during the break, and I show you.
Yeah.
Sure,
thank you.
All right, let's thank our speaker one more time.